My honour to introduce my boss, because Roger Riddell is the director of the Children's Medical Research Institute next door. He's the Lorimer Dodds Professor at the University of Sydney, and he's the one who convinced me to apply proteomics to cancer. So he and I are co-directors of ProCan, and he's going to give you an update on where ProCan is at the moment. Roger.
Thanks very much, Phil, and great to see everybody here. Many of you have collaborated with us and or supported us and helped us in many different ways. So it's fantastic to have the opportunity to discuss with you where clinical proteomics may go, hopefully in the very near future. What I'll try to do today, and please excuse my croaky voice, what I'll try to do today is not go deep into any of the data that we've generated, but to give you an overview of what we've been trying to do for the last 7 years, and in a way to set the scene for the discussion that I hope we'll pursue throughout the day, and particularly in the last session of the day, about how to take proteomics into the clinic, how to do true clinical proteomics. So this has been a 7-year journey for us. In fact, it started in 2015 when we pitched to the Australian Cancer Research Foundation, whose logo is on the opening slide here, the idea that we would generate both the technical capability and the knowledge base to allow us to take proteomics into the cancer clinic. So this has been a wholly translational project right from the beginning. The sole aim, if you like, or the overwhelmingly major aim of the project has been to develop the technology that's clinically relevant and to try to find the fastest possible route into the clinic. Now, I think with the people in the room, you probably need no convincing at all that understanding the proteome of cancer is critically important. For at least 5 decades, medical oncologists have been using measurements of individual proteins or very small panels of proteins to help them make treatment decisions and to understand what is the likely outcome of treatment or just prognostic indicators for individual cancer patients. One of the very earliest of these, of course, is the estrogen receptor, which has been used for 5 decades now to guide treatment decisions about the use of anti-estrogens in breast cancer. And just show the sort of amazing AlphaFold predictions on the top of the slide here. But what you can see is what is currently used for measuring estrogen receptor, which is immunohistochemistry. Actually, when I was a trainee medical oncologist, what was being used was biochemical methods, which were quantitatively much more accurate at a tissue level, but of course don't have the same spatial information that you get from looking at immunohistochemistry. And then if you measure estrogen receptor levels, it is predictive at about 70% accuracy of whether a breast cancer will respond to anti-estrogens. If you add in progesterone receptor, that increases the accuracy a little. And of course, what's also come along in more recent years has been HER2 measurements, which give a whole set of additional information about the patient and the likely response to various types of treatment. Emma Boyes, who's one of the medical oncologists who's doing a PhD in the ProCan program, reviewed the literature 6 years later after we started to see to what extent proteomics has entered the cancer clinic. and the answer, at least at the routine level, is close to zero. There's almost nothing in terms of proteomics that's routinely entered the cancer clinic. There are some very limited exceptions. There's thyroglobulin measurements which are available in North America, but with very limited exceptions, the conclusion as of last year was that mass spec-based proteomics has not yet been implemented in routine clinical practice. Many of you in the room are aware of why this is, and I won't go into all of this, but there have been issues with reproducibility, from one platform to another, or even from one instrument to another. The preparative techniques which have been used in the cancer proteomics field, although they have yielded some outstanding biology papers in understanding the proteins in cancers, mostly, at least when we started this, the preparative techniques were not suitable for routine clinical use. And most of the studies, and this is true to this day, most of the best cancer proteomic studies which are published in the literature weren't really designed with clinical questions in mind. It was more about the cancer biology. This, and Rosemary Berlin, who's in the room, may remember pitching to the Australian Cancer Research Foundation. Rosemary very kindly joined us on our side of the table, and incidentally, her presentation to the ACRF committee, the Australian Cancer Research Foundation committee, which was judging the equipment grant that we had applied for, was mostly about things like the extracellular matrix that we've just heard about, and why understanding that is particularly the domain of proteomics, and all of the reasons why understanding the matrix and the tumour-associated, supposedly normal cells would contribute a lot to our understanding of the outcome of cancer. This is what we proposed to the Australian Cancer Research Foundation back in 2015, that we would use the equipment that we're applying for from the ACRF in a $10 million grant to essentially deliver to cancer clinicians a report of the nature that's shown on this slide. So the elements of the report were, of course, there's information up the top there. That's information accompanying the specimen. So name, medical record number, and the anatomical site that the specimen had come from. What we suggested that we would do would be to deliver a report within a couple of days, and I'll explain in a moment why we had that as our goal. And what you can see here is that, what I put on that slide was, a sample receipt date of 26th of August 2020 and a report date two days later. So at that stage, we were essentially promising that we'd get through this entire program in 4 years. Now, we've failed on that one, but I hope to persuade you that we've made substantial progress on most of the other things that we pitched. So in addition, what we would do independently of the histopathology would be to come up with a proteomic classification of the tissue and cancer type, and perhaps come up with a new proteomic classification. Then, because there is this history of many decades of medical oncologists relying on the measurement of single protein biomarkers, we anticipated that our report, for the foreseeable future, would need to include all of those proteins that the medical oncologists know and love and rely on. and that maybe there'd be some additional single protein biomarkers that we'd add to the report as we went along. But perhaps the most important part of this would be outcome predictions, where we would use combinations of proteins to predict treatment response. Now, we can already predict response to antiestrogens with about 70% or a little better accuracy, but by putting multiple proteins together in a signature, we'd like to push that up to, towards 100% accuracy, etc. Response to PARP inhibitors, and things that we predict that the tumour is not going to respond to. So treatment response predictions based on proteomic signatures. So I will, okay. So what I will do is go through those 4 elements of the report in order over the next 15 or 20 minutes and just give a high-level overview of what progress the ProCan team has made. So the first one was a report in 2 days, and I'm very happy to say that we have the technological capability of doing exactly that. That's been a major success, I believe, of the team. Why 2 days? And the reason is that in oncology, I mean, it's one of the few medical, well, it's probably the only medical area where starting treatment for cancer almost always relies on a piece of tissue being taken and sent to expert anatomical pathologists for examination and a report. And typically from the time of the biopsy or the excision biopsy being taken and being processed, typically through formalin fixation and paraffin embedding, staining, and then reporting by an expert pathologist, about the minimum time for that is around 2 days. So our aim was to come up with a proteomic matrix, a protein matrix, and a proteomic report within the same period of time. At the time we started, it wasn't clear to us, or at least it certainly wasn't clear to me, that it would be possible to do this at very high quality level from FFPE material, formalin fixed paraffin embedded material. And I think one of the achievements of ProCan and the field, and not just ourselves, has been the demonstration that you can in fact get high quality proteomic data from FFPE material. What this means is that all that is required, so even though in a sense, we're hoping that this will be disruptive technology, it will have almost no disruption on the clinico-pathological workflow, because all that would be required would be for an additional section to be taken when the pathologists are taking a thin section to put on a slide for examination. We would be asking for one additional section to be put in a tube, and for us to be able to deliver a report within the same time period as the pathologists do their report, so that the combined information would be available to the treating clinician at the time of the first post-biopsy consultation, when treatment decisions, it's the earliest possible time when treatment decisions can be made. Now, of course, it's one thing to develop the technology to do that, measure a whole lot of proteins, and I hope to persuade you that we can do this very well. But it's another thing to be able to interpret that for the benefit of the patient. And you heard Amelia's outstanding presentation about the dissection of the meaning of the extracellular matrix, what that might mean for the patient. So there's a whole lot of work that needs to be done to build a database of proteomic and clinical data, so that we can use the proteomic data to make meaningful predictions in a clinical sense. So there are essentially 2 parts to the project. One is to develop clinically relevant high throughput proteomic technology, and the other is to build a major pan-cancer database of proteomic and clinical outcome data. To do this, we needed funding, and we're very grateful for all the funding agencies that have helped us with this. I've mentioned the Australian Cancer Research Foundation, which was pivotal in getting us the equipment. Our first major operational grant came from the Office of Health and Medical Research and Cancer Institute in New South Wales, who've been fantastically supportive, but there have been many other agencies that have helped us tremendously. And of course, we needed a team, and we are very fortunate to have many exceptional individuals in a large multidisciplinary team now in anatomical pathology. So I mentioned Rosemary earlier on, and as a fully qualified research anatomical pathologist, Rosemary guided the setting up of the program over the first 5 years, for which we're very fortunate. Outstanding proteomics team, software engineering, data science, of course. This is essentially a big data project. Project management, ethics and legal have been critically important. And in recent years, we have an outstanding medical oncology team. We've also been immensely aided by our ProCan Consumer and Community Advisory Panel. And they're not officially members of the team, of course. They're independent oversight, but the Human Research Ethics Committees and the specially convened document review committees that deal with the ProCan documentation have been pivotal in helping us. We've put a huge amount of effort, and this really took the first 3.5 years or so of the ProCan program in developing a very efficient and reproducible sample pipeline. I won't go into the details of this. There are multiple steps. It can be completed so that the total elapsed time is a matter of hours. This is delivered in spades, if you like, on the aim of being able to do all of this within a 2-day window. Huge amount of effort on quality control. I think this is something that's really been distinctive about what the ProCan team has done, is to really focus on quality. And again, I won't go into the details of this, but this slide just illustrates that bovine serum albumin calibration is run frequently so that the team knows in real time whether the instruments are behaving properly so that valuable samples are not lost. In addition, human cells are run, so HEC293 cells, as large batches of these are grown in a bioreactor so that they're there as a standard that control both for the whole pipeline and also for the mass spec running. So these are run on each instrument every day, and they're a very important part of the quality control. I won't go through this because it's been published back in 2020, but a lot of work was put into understanding how to run 6 essentially identical mass spectrometers, and more recently we've acquired a 7th of the same type, how to run them reproducibly over long periods of time. In this experiment, multiple standards were run over 4 months, and the computational methods that are required in order to get reproducible data over that time. Critically important to the success of the project. And then more recently, this is unpublished, but work put into assessing how reproducible the data are over longer time periods. And what I've illustrated here is that at least at this dimensional reduction level, the data cluster nicely together, even with samples that have been run up to 3 years apart. Okay, so that completes that section about the technical capability that we've generated to deliver a report within 2 days. But what are we doing about interpretation of the data? So the next point on that list is proteomic classification, and I'll just touch on that briefly because although we've made good progress on that, it's still very much a work in progress. Hoping that we will have a manuscript submitted on this within the next month or 2. But one of the things we need to do is to be able to predict the cancer type and subtype, and at several levels. So one would be classifying the tumours according to their histopathology. How accurate are we at predicting what the histopathologists see down the microscope? Plus also, and I won't touch on this today, but what else can we do in coming up with new classifications that are meaningful in terms of predicting outcome? So what I've described so far is really strategies for achieving large-scale proteomic data. So being able to acquire data continuously over long periods of time, being able to harmonise the data from multiple instruments, and being able to, I didn't mention this, but being able to obtain data from multiple storage types. Fresh, frozen, stored in OCT, FFPE material, etc. So this is really important about assembling a lot of data, which is what we really need to do in order to come up with classifications such as cancer type. So over the time of the ProCan project, we've run nearly 23,000 cancer specimens from more than 100 cancer types. The way this works is that the samples come in here to Westmead. They come in from multiple sites around the world, so this has really been a hyper-collaborative project. We have currently, at last count, we have 112 formal collaborative research agreements in place, 78 within Australia and 34 essentially in first world countries, so North America, Western Europe, UK, and Japan, on the understanding that the outcomes are going to be more or less similar in health jurisdictions that have got comparable health systems. And this is the only slide that I'll show on this subject, this is work of many people, but particularly Simon Kay. So one of the approaches that we've taken is to start with cancer cell line data and then fold in relatively small amounts of real tumour data by a machine learning approach called online machine learning, just to determine how accurate we are at predicting cancer type, and that's on the left. And you can see that at least at the top 3 accuracy level, we're up over the 97% mark, which, as some of our pathologist colleagues have pointed out, is probably about the accuracy of histopathology also. A more challenging project is predicting, for an adenocarcinoma, predicting what tissue it came from, and as you can see, we're doing reasonably well on that. Okay, all right, so getting close to the end now, but the third element of the proposed report was quantitative mass spec data for individual protein biomarkers, for which there's already a very substantial body of evidence. This is the work primarily of Erin Sykes and others in the proteomic team. Erin has led this, and this is quantitation of estrogen receptor in breast cancer samples, and I won't go through the details of this, but what you can see is that there's a good correlation between the quantitative mass spec measurement of estrogen receptor and the assessment of estrogen receptor based on immunohistochemistry. And then just one other of many other possible examples that could be shown is the quantitation of HER2 in breast cancer and you can see that there's a good correlation between the immunohistochemistry reading and the mass spec reading. In all of these things, of course, there's a problem with what is the gold standard. And if there's a discrepancy between the immunohistochemistry and the mass spec, how do you assess which is correct? In the case of HER2, we have the advantage that there's also in situ hybridization data available for many of these. Among the 6 where the immunohistochemistry and the ISH don't correlate among themselves, SRM is consistent with ISH in 4 of those 6 cases. In situ hybridization is generally regarded as more accurate in this context. So finally, just like to touch on this final point about treatment response predictions based on proteomic signatures. And I'll just show a couple of examples. Many of you in the room have collaborated with us on these projects, but I'll just show 2. For each of these predictions, we're really focusing on individual clinical scenarios, on the assumption that the background genome, proteome, etc., for that tissue type is going to be very important in the prediction. So each of these projects is individual. So early stage ER-positive breast cancer is a separate project from looking at early stage HER2 positive breast cancer and so on and so forth. And that's just breast cancer. So of course, prostate cancer, many other cancer types. So we're assembling this essentially as a jigsaw puzzle of many different cancer types, for each of which we're endeavouring to come up with predictive and/or prognostic signatures. So the experimental design for each of these is that we go to collaborators to acquire a cohort that's designed to answer a high-value clinical question, which our collaborators help to define. Obviously, there must be suitable associated clinical data in order for us to make the predictions, and we prefer collections that have got other omic data as well. We don't assume that the proteome is going to have all of the information that's required, and we like to be able to compare and contrast with other omics. This is one example of a project which is under review at a journal at the moment, papillomavirus positive oropharyngeal squamous carcinoma, in collaboration with a surgical oncologist in Brisbane. And what you can see is that we've been able to come up with a proteomic-based risk score that stratifies the patients according to very low risk of recurrence, intermediate risk, and high risk on these Kaplan-Meier plots. And then similarly with early stage lung cancer, where if it's surgically resectable and it's early stage, most of these patients are cured, and so mostly they're not treated with adjuvant treatment, but some of them do relapse and would have benefited from adjuvant. So being able to predict is very important. And this is a collaboration with Kurt Harris and Eitan Rupin at the National Cancer Institute in Bethesda, Maryland. And we've been able to define a 12 protein risk score, which stratifies the patients, as you can see here on these Kaplan-Meiers. And that's being validated in 2 cohorts in Sydney, one from Royal Prince Alfred Hospital and one from Nepean Hospital in the West. Of course, every one of these clinical cohorts is a single experiment. And we'd like to be able to obtain much more data. So we're also working with cell lines. So not just tumour tissue, but organoids, cancer cell lines, and so on. We published this last year in August, a pan-cancer cell line proteomic map that, with a whole lot of treatment response data. So this is where we're up to. We've made substantial progress for each of these 4 areas of the proposed report. It's required an amazing team, and I acknowledge Phil Robinson, who's my co-director of the program, Adele, who is our lead medical oncologist, Karina in project management, Michael Dousman, who leads our awesome software engineering team, Peter Haynes, who leads our equally awesome proteomics team, Ching, the data scientists. I mentioned the ProCan consumer panel. These are the collaborators that I've mentioned in the course of this presentation, but there are hundreds others. And special mention to the former team leaders, Brett Tully, Rosemary Boleen, and Edith Hurt. Thank you very much for your attention.
Thank you, Roger. Thank you, Roger. There's time for a couple of quick questions if we have any. And there's plenty of time for conversations. Go ahead.
Roger, I just wanted to ask about the start of the presentation. You're talking about being able to get the report back within the 2-day period, which I think is a really important, valuable step. I'm just wondering, have you done a pilot study now where you've been able to run the program for a number of months and meet that objective? And then perhaps you might tell us about how that's been a challenge in different tumour streams. Has it been the same across tumour streams?
No, so the short answer is we haven't tried to do that. So we're still at the level of doing cohort studies where we wait until the whole cohort has been assembled, and so essentially we're not at the point where we would even have mass spec readiness for samples coming in and turning around. This is something that we're working on over the next 12 months to get to the point where we would be ready to be able to turn actually be ready to go and actually deliver within the 48-hour time period. What I've glossed over, of course, is that for it to go into the cancer clinic, it will need to be signed off by a pathologist, and we're in conversation with people, or at least one person who would be very suitable for doing that. But so 48 hours, even though the elapsed time is much less than that, 48 hours will still be quite a logistical challenge.
It'd be an incredible, valuable study, wouldn't it, to be able to demonstrate the challenges in doing that?
Yep.
Yeah, thanks, Mark. Any other questions for Roger? Okay, well, we'll leave it to discussions. Thanks very much, Roger, again.